Hello. Am I audible?
Yes, you are.
Okay. So let's wait for 1 or 2 minutes more, then we'll start. नहीं कैमरा स्टार्ट. Hello, is my screen visible?
Yes, sir.
Yes, sir.
Okay, so my name is Dinesh and I'm from University of Hyderabad, and I'm the TA for this course, Quantum Mechanics and Molecular Spectroscopy. So we'll do some problems related to week 1 of this course. So I hope all of you attended sir's class. So for this for today's class, I see I can't write on screen, so we'll do some basic problems today where we don't have to write much, and next class onwards we will do some numericals based on the class. Is that sounds okay?
Yes, sir.
Okay, so we'll start from some basic questions of quantum mechanics. So, I can't write. So okay. Mm, as you know, in quantum mechanics, the observables are denoted by operators, and they act on some wave function which is not physical. This wave function, what this wave function does, so this wave function describes the behavior of the particles, its position, momentum, energy, all the physical observables, whatever you can imagine. So this wave function, this can be complex in general. So this is not a real wave function. So we can't observe this wave function. We can indirectly, um, this is a tool, just mathematical tool, so we can use this wave function to do our mathematics and compute the observables like energy, position, momentum, etc. So as this is a wave function, so it's vaguely saying, so it's a wave, so it should satisfy some wave equation, right? So you might be knowing on this wave equation, which is in second order in time and second order in space. Generally, in classical mechanics, you can find those equations which will be satisfying the equations which will be second order in time and second order in space. But um, in, similarly, in quantum mechanics also will have some wave functions psi which will satisfy some wave equation. Okay, so this wave function, this can depend on position and time. Okay, so I assume all of you know basic quantum mechanics, so and you also know about Schrodinger wave equation also. So can anyone tell me which of these four options is correct for Schrodinger wave equation? Classically, this wave equations are in second, they are same order in time and space also. You can see from the left hand side, uh, this is first order in time, this is first order in space, but Schrodinger equation, it looks something different. It is linear. That means I can operate by linearity. I mean I can let's assume I have an operator A and I am applying on some states A plus B, or let's rename it X plus Y. So this operator A will act on these states linearly. That means A will operate on X plus A Y. So it's hard just by saying. Um, Let me try once. Okay, it should work. So wave function. Oh, okay. Okay, so just follow my words. This psi depends on position and time. So in quantum mechanics, position uh, is an operator. Classically, it's an observable. You can observe a position of a particle. Classically saying, like you see a ball, we can determine its position, momentum, and certainly we can measure its energy also. Like depending on its position in space, we can determine its kinetic energy, or by knowing its height from the ground, we can determine its potential energy also. So similarly, those roles are played by wave function in quantum mechanics. Okay, so Schrodinger equation is a wave equation, and it has a property like it satisfies a linear operator, which is first order in time and second order in space. So what this equation is saying? So this equation is suggesting how this wave function is changing with respect to time, and how it is changing with respect to the space coordinate. Okay, so which will be the right answer? This will be D. Okay, there is H cross is there. So you can identify this d over dt and IH cross. This differentiation, it is an operator actually. So what kind of operator it is? Can anyone tell me? This is a energy operator. Anyone was trying to say something? So I'm really sorry I can't write today, so it will be fixed by next class. So this d over dt, it's known as energy operator.
So can we say it Hamiltonian operator?
Yes, Hamiltonian is a form of and what is Hamiltonian in quantum mechanics? Its eigenvalue is energy, so it's energy operator, right? Hamiltonian describes the energy, like Hamiltonian is the sum of uh, kinetic energy plus potential energy, right? Hamiltonian we can write as T plus V. T is kinetic energy. So, are you suggesting group, like WhatsApp group? Nagaraj, can you speak? I don't understand this comment.
Yeah, no, sir.
Um, what are you suggesting?
No, actually, if we get the contact number of others, those who are the attending, so that it is useful to discuss.
Oh, okay, okay. Yeah, yeah, sure. If
That's what
means,
the
yeah, yeah. You
yeah,
guys can discuss whatever
yeah,
question you have, or if you have any doubts, you can just ask me through my
yeah.
mail ID. Uh, I hope you all have my mail ID.
Okay. Share, Professor, one more time your mail ID in that chart.
Okay,
No.
I'm writing it in this chart. Okay, so if you have any questions, you can simply mail me. I'll be replying you here. Okay, okay, let's continue. So here, this d over dt, this is the energy operator. And can anyone tell me what is this d del over del x represent in quantum mechanics? Like with some constant I h cross minus I h cross del over del x. What this operator represents in quantum mechanics? It's momentum operator. You see, del over del x is momentum operator with some I h cross minus I h cross actually. So you see there is del square over del x square with h cross square. So it is p square. Actually it's px square. That means it's momentum in x direction and divided by 2, p square over 2m, and the left hand side is E, energy. So you see, um, non-relativistically you can like express uh, p square over 2m as kinetic energy, right? P is mv, right? So if I do p square, then it will be m square v square, and if I divide by 2m, then it will be mv square by 2. That means half mv square, right? So half mv square is kinetic energy. Okay, so this part is kinetic energy. Okay, and plus u psi, this operator u is potential energy. Okay, so kinetic energy plus potential energy is the total energy. This left hand side is total energy, right? So Schrodinger equation is kind of non-relativistic equation. Okay, so if you go see, if you study higher advanced quantum mechanics, then you will see there are some equations with second order in time and second order in space. We call those equations as Klein-Gordon equations, and you will also encounter first order in time and first order in space. We call those equations as um, Dirac equations. So those are relativistic equations. That means what? When the particle speed is near to the speed of light, then it acquires some um, like the dynamics will be different compared to the non-relativistic case where the particles speed are very less compared to the speed of light. Okay, so for non-relativistic case, the particles obey this non-relativistic kind of equation, which is known as Schrodinger equation. Okay, where this psi is the wave function describing the properties of the particles, and these derivatives are the operators in quantum mechanics. The change in space, um, this operator represents the momentum, and this derivative with respect to time, it represents the energy. Okay, and you see it's satisfying, and total energy left hand side E is equal to p square over 2m, which is half mv square, which is the kinetic energy, plus u, which is the potential energy. So total energy is equal to kinetic energy plus potential energy. Okay, so correct answer for the Schrodinger wave equation will be D, because it has second order yeah, here also one second order in space is there, but one h cross is there, it should be h cross square, so to be dimensionally correct, so the correct answer will be D. Here you see the second order derivative with respect to space and first order derivative with respect to time. Okay, so the correct answer will be D. Any questions till now? You have doubts with this? You can just ask me. Okay, so I assume there is no doubt, so I'll move to the next question. So these are basic questions because we are going to study time dependent perturbation, so we must know these basic properties of quantum mechanics, like the basic things, wave function, um, like observables in quantum mechanics, those things. So coming to the next question, for a quantum wave particle, what is the energy? That means what will be the discrete energy actually. So you know, classically energy can be continuous, but when you go to the quantum mechanics case, energies are not continuous anymore, they are packets of energy now. So energies come as a packet form, means they are discrete, so they will have some certain values of energy, they can't be just continuous values. So if you have a system like particle in a box, it can't have all the possible ranges of energy, it will have certain values of energy. That means the particle can have some minimum energy, then next some like this, see if a particle in the ground state have some energy, let's say E1, then in it can have, okay, someone already know the answer. Okay, it won't be h cross k, it will be h cross omega. K is like wave number, you can check, and h cross will be dimension of angular momentum. So angular momentum dimension is e times time, so we need a coefficient like which will have inverse of time. So omega is the frequency, where this k is the wave number. So k is basically 1 over lambda, and omega is the frequency, is basically 2 pi over time. So omega will have dimension second inverse, whereas this h cross will have dimension as energy times time. So energy times time into time inverse will give us energy, whereas this, if you check energy times time into meter inverse, so it won't give us energy. So the dimensionally correct answer will be h cross omega. And as you might be knowing from the what is the photoelectric effect. So you know, energy of photon will be h nu, right, where nu will be the frequency of the light. So where this omega is the frequency, so the correct answer will be h cross omega, right? And if the question was asked like particle inside a trapped box, then what will be the minimum energy for that particle? In that case, it might be half h cross omega, but the question is only what is the quantum wave packet of this energy form. It's just simply h cross nu or h cross omega, right? It's just photoelectric, from photoelectric effect you can just correlate this, like energy of a photon particle will be dependent on the frequency of that light or frequency of that wave. If it is nu, then its energy will be h cross nu, right? Or you can express it is wave, like it can write also in wavelength also, like there is a relation between speed of this wave and the frequency and wavelength of this wave. Like if frequency, we can denote it as f, then and wavelength is lambda, then lambda times f will be equal to the speed of that wave, right? You might be knowing this. Lambda times nu is equal to c, where c is the speed of light, lambda is the wavelength, and nu is the frequency of that light. So the waves which are traveling at speed of light, so depending on the frequency of that wave, we can categorize all those waves in different spectrum. Like in visible range, that which we are seeing around us, it will have some frequency range, which we call them as visible light, right? Okay, so above that, with higher frequencies, will enter into ultraviolet light, gamma radiation, those kinds. Increasing the frequency, the energy of that light or waves will be more. They also come as packets, and their energy will be depending on their frequency. Okay, so, and our body also radiates some kind of waves. You know which kind of wave our body radiates? Can we see those radiation? Does anyone know what kind of radiation our body emits all the time? It's infrared actually. So we can't see infrared. Humans only can see visible light with certain frequencies. Infrared light will have less frequencies and high wavelength. We humans can't see them. And ultraviolet lights which are coming from sun with higher frequencies, that means they have high energy, that those waves also we can't see. We only can see certain range of waves which we call visible light. Okay, so ultraviolet violet light also we can't see, which are coming from sun, and the infrared light which have lower frequency, that those lights also we can't see. So the relation is just h cross omega, as just elaborating other stuff. Okay, so the answer is h cross omega. It's the quanta of energy which is discrete, which comes as a packet, which unit is h cross omega. If omega is different, like for visible light, omega, let's say for visible light some nanometers of wavelength is there, and its frequency is some hertz, let's say it's 10 to the power 9 hertz. I'm just saying it vaguely. You can check its frequency and wavelength, and for that energy will be h cross omega, where this, if we increase this frequency more, going to ultraviolet range, then h cross omega will have value more. That means energy of that wave will be more. So you might be knowing, like the energy comes in a packet which we call quanta, right? You I am assuming you all are aware of this black body radiation. From there we derive this sense of quanta of energy, like energy is not continuous anymore, it comes in chunks, like small packets, and it will have some certain values which will depend on the frequency of that radiation. Okay, so you can imagine this is a wave in a packet form, like this wave will overlap with itself and it will move as a packet with some certain energy which will depend on its frequency. Okay, frequency means the number of waves passing in 1 second, right? Then frequency is more, means more number of waves are passing in 1 second. Okay, so you can just get a mental picture. The more number of waves passing in 1 second means it will have more energy, right? So the quanta of wave packet will be h cross omega. Okay, so any questions till now? I'm sorry I can't write this time, otherwise it would be better.
So actually, when this energy will be h cross omega by 2?
You can get this example. Particle in a well, in a potential well, there this minimum energy can be half h cross omega. Half is just a number, and this minimum value can be half h cross omega, but the quanta is just h cross omega, right? It depends on the frequency, and h is a constant. And h cross is a fundamental constant. Okay, so the only thing, this energy depends on the frequency of that wave. Okay, right. You know about duality nature of light. Light sometimes behaves like a particle, and sometimes behave like a wave. So you might be aware of this de Broglie wavelength phenomena, like any particle can have wave nature, right? And the best example is electron. Electron you can imagine as a point particle, or you can imagine as it as a wave, right? Depending on its mass, the wavelength of that particle we can calculate from this de Broglie formula actually. So all the particles we see around us, they have both wave and particle nature. So depending on their wavelength or frequency, we can calculate the minimum energy they can possess. Okay, so this half h cross omega will come when that particle will be trapped in some potential, like potential well. We can see maybe in next class I'll show you, but the fundamental quantity is just h cross omega, right? So the energy comes in packets as h cross omega. So as omega varies, the energy of the particle will vary, right? Okay, so moving to the next question. Okay, Schrodinger wave equation can be derived from principle of quantum mechanics. Is it true or false? Can we derive Schrodinger equation from any quantum mechanical principle? Any guess?
No, sir.
Can you derive this Schrodinger wave equation? Like this, I told you this non-relativistically energy should be equal to kinetic energy plus potential energy, which will be p square over 2m plus b. Okay, where this E you can write as d over dt, where p square by 2m you can write IH cross del square by del x square, and this potential you can keep it as it is. But there is no derivation for that. It's a fundamental principle. You can just verify it. Schrodinger itself, he didn't derive it. That equation came as an intuition to him. He just can't derive Schrodinger equation from anything, any quantum mechanical principle. It's just intuition. He come up with this equation, like non-relativistically energy will be equal to kinetic energy plus potential energy, like that. So we can't derive Schrodinger equation. It's a fundamental equation which is just there. We can verify it, we can't derive it. Okay, so it is false. We can't derive Schrodinger equation. It's a fundamental principle, and fundamental principles can't be derived. Like in mathematics, you have to take some assumption, right? That assumptions, or you call it as lemma. You don't derive those lemma. It's just there. Based on those, you do other mathematics, right? Similarly, Schrodinger equation can't be derived. It's a fundamental principle, fundamental wave equation. You can verify it, but you can't derive it. Okay, so the answer will be false. Understood? If you think you can derive Schrodinger equation, then you can try and tell me in next class how you derived Schrodinger equation. We'll all discuss about that then. Okay, moving to the next question. Okay. The question is, find the function f of x for which this x f of x is equal to minus I by h cross a square px f of x. So it would be better if I can write or you can do one thing, you just substitute this p of x as its operator form. Like, what is the operator form of this px? Minus I by h cross, I guess, I by h cross del by del x. Constant part I don't know, I by h cross or I h cross, something will be there, but this will be in differential form, del over del x, right? So you substitute this as del over del x, then you do variable separation. Okay. Maybe this question I will solve in next class. Now you just follow my words. You can take pen and paper and substitute this px by del over del x, then it will be del f by del x, right? Then you take this denominator del x to the left hand side, and you take this fx to the right hand side, so it will be del f by del f, and on the left hand side it will be x into dx, right? Then you can do integration on both of the sides. Integration on both of the sides, then the left hand side will be x square over 2, okay, and the right hand side will be this constant minus I by x cross a square logarithm of f of x, okay, and px will come with I h cross, I guess, so it will cancel with this minus I, so I will cancel with minus I, and minus I into I is 1, and h cross will cancel with this h cross, which will come from this px. So you will have x square over 2 on the left hand side, and on the right hand side you will have log of f of x and multiplied with this a square. Okay, then you can take this a square to the left hand side, then you will have x square over 2a, right? Sorry, a square, x square over 2a square on left hand side, and in the right hand side you will have ln of f of x. Then what you can do, take e to the power of both left and right hand side, then you will have on the right hand side f of x equal to e to the power x square over 2a, obviously with one minus sign. So I think px will be minus I h cross, then it's minus I, so ultimately you will have a minus, so it will be e to the power minus x square over 2a square plus some constant, or you can take that constant as k. I guess you can all do this, or in next class I can solve it to you. So the right answer will be this. It's just solving a differential equation, so the right answer will be minus x square over 2a, this one, C. Any questions? Somebody who couldn't follow? This is simple differential equation. You have to do variable separation. You have to take x one side and f of x to different side, and you have to just substitute this px as its operator form minus I h cross del over del x. Then you separate del x to x side and fx to this fx side, then you have to just integrate, then you will get this answer C. Okay, just interrupt me if you don't.
That's it.
Yeah, okay, moving on to the next question. Yeah, okay. any wave function can be written as linear combination of what? Any guess? Just guess it and the answer. Then I'll explain.
So B
Eigenvalues.
eigenvalues.
A wave function. It's a function, right? Okay. Okay. So it's a wave function, right? So if I am writing this wave function as a linear combination of something, the other side also have to be a function, right? So ultimately it should be a function. So the correct answer will be C, eigenfunctions. Any wave function can be written as a linear combination of eigenfunctions. So like an operator, okay, let's assume a operator A operating on a wave function psi, and it will give a expectation value, let's say small a, with that same wave function. Those kind of equation we'll call as eigenequations. Okay, where this wave function won't change and it will scale as the expectation value of the operator, right? So you can say there are you can analogously imagine them as coordinates in Cartesian coordinates. These axes x, y, z, and z. So you can imagine operating the operator as stretching, like the action of operator is stretching. So if you have coordinates like x, y, and z, if you assume this operator a as action as of stretching, then if you apply some force on x-axis, it will stretch, right? If you I can draw, just imagine if you pull the x-axis of car, or imagine elastic band, it's keeping it as on a straight line, and you are pulling the other end, it will just stretch, right? So but its direction you don't change, just pull it in one direction, what will happen? It will stretch. So this stretching is an operation, right? So what is this operation doing? It's okay, let's assume elastic band, you cut it in half and just make it a line, and you put a point on this elastic band with a pen, and you stretch it. What will happen? That point will move in this direction, right? So what is the stretching do? This stretching operation, it will move the point along the x direction, or you can just imagine a car moving in a straight line. So moving is an operation, what it is doing? Changing the position, right? But the direction is not changing. The direction not changing is a special thing actually. My so visually I can show you in the next class. So not changing direction is a special thing in quantum mechanics actually. So just imagine stretching is as an operation. By this stretching, what I am doing? I am changing the position of a point in this elastic band, right, along this same direction. So the amount this point is changing, let's say it was on position 1, after stretching it will go to the position 2. So this point shifted by 2 units. So this 2 units is a value, but the direction is not changing. So you can imagine this directionality of this axis as a function, and the value 2 is a value by which this axis is not changing, but the value is the point is shifting. So like okay, so promise I'll fix it in next class and it will be better. So just take my words. Directionality, like you imagine in Cartesian coordinate space, direction of any vector after applying some operation, if it is not changing, that's a special case actually. But the length of that vector is changing, the amount by which it is changing is known as its eigenvalue, and that vector's direction or that vector itself is known as eigenfunction. So eigenfunction is a special thing in quantum mechanics. You can imagine this eigenfunction as coordinates x, y and z coordinates in a Cartesian coordinate system. So if you draw any line in this coordinate system, you can express this vector as a linear combination of this x, y and z coordinates, right? So this x, y and z coordinates are wave function which are not changing with their direction, but this scalar which we are multiplying with that direction, it's just scaling in that same direction. That scalar which is multiplied is known as its eigenfunction, eigenvalue, and that vector itself is known as eigenfunction. So next class I can show you graphically. So any wave function can be written as linear combination of eigenfunctions, or you just analogously can say any vector can be expressed as linear combination of x, y and z direction. So similarly, these eigenfunctions are the basis vectors in some arbitrary space we call as Hilbert space with some arbitrary dimension. There can be some n dimension to that. N dimension means n direction it can extend. So each direction is a special if it is not changing its direction, or each function if it is not changing after some operation is special. If it is not changing, then that function is called as eigenfunction, and the value after this operation we are getting is known as eigenfunction. So any function can be expressed as linear combination of this eigenfunction, and if one function is changing after applying some operator, then it's not an eigenfunction, it's just a function after this operation is changing, affecting it the wave function and making the change in its value, then it's not a wave function, means eigenfunction. So the quantities which are not changing actually are special in quantum mechanics, and we can apply some operators on those wave function and we can get some eigenvalues, and those eigenvalues will be some observables in quantum mechanics. Like there is a wave function psi, let's say psi 1, and we are applying this Hamiltonian on this psi 1 or this energy operator. So what you will get as eigenfunction? Energy, right? So I am applying H on psi 1, I will get E1 psi. Okay, so this psi is not changing, but it's giving one value E1. So E1 is eigenvalue, and the function on which we are applying, doing some operation, is known as eigenfunctions. Okay, so if I apply some x operator, x care, on this wave function, what it will give? It will give me the position value, like let's say a value, but the wave function will still remain same. So this wave function can as that wave function we can say eigenfunction, and the value it is giving us we can call it eigenvalue of that operator. Like if I operate momentum operator on this wave function, what it will give? The momentum eigenvalue along that wave function. I guess you understood that. Or I can show you in next class. It will be better if you visualize this. It's a special thing actually in quantum mechanics, eigenvalue and eigenfunction. I guess everyone understood, so I'm moving to the next question. Okay, which of the following can be a solution to Schrodinger equation? Can anyone guess it? Just guess which one is acceptable. So the wave function, it should satisfy some condition, otherwise it will give some peculiar answers if we plug in Schrodinger equation. Like you see the first example. What is the problem with this? It's continuous, right? It's not cutting anywhere. Can we differentiate this curve? Any guess? We can differentiate this curve, but there will be some problem at this point. If we differentiate this curve at this point, what will happen? What is differentiation anyway? If you are differentiating any function, like say this function, if I am differentiating it at this point, what it will give? It will give me a slope at that point. Okay, let's say I am differentiating this function at this point, it will give me a slope at this point. Okay, it will be tangent to this curve at that particular point. Okay, so I can do differentiation at any point, but when I'll come to this point, what will happen? What is the slope at this point? I can like the slope will be in this direction for all of these points, but as I am reaching this point, the slope will be undefined actually. Suddenly this curve is changing here, so at this point the slope will be undefined. You can do differentiation at this point. It's suddenly changing. This derivative will be undefined. So if the derivative is undefined at this point, if I put the derivative in the Schrodinger equation, the Schrodinger equation will give me some bunch of infinities or some absurd results. So this kind of curve are not acceptable because it's not differentiable at this point particularly. And what is the problem with this? It's continuous. I can differentiate at any point. Any guess? If you draw a vertical line here along this direction, what will you see? You'll see it is multi-valued. At a particular value of this, let's say x direction, you'll have two solutions in y direction. Okay, in this region, if you draw a vertical line, you will get two values for a single value of x. So it's a multi-valued function. So what is the problem with multi-valued function? If you put this in Schrodinger equation, it will give two values. Two values can satisfy the Schrodinger equation. But when you solve the Schrodinger equation, then what will be the solution? You can't simply do the inverse and find one point. Like just imagine this is the curve. I am putting this in Schrodinger equation. By Schrodinger equation, what I will get? I will get this function psi, right? The Schrodinger equation is a equation with respect to psi, right? So if I solve the Schrodinger equation, what I will get? I will get this function psi, right? So if I solve that Schrodinger equation and I have the solution like this, but then in that case I can say which will be the solution at a particular point because it is multi-valued. But if I check this curve, if it is the wave function, if I solve the Schrodinger equation, I will get single value for a single point. Like say this x-axis is position, x direction, and y-axis is psi, right? So if I solve the Schrodinger equation, I will get psi. Okay, then that psi I can plot with respect to x or t. That's psi wave function. It depends on position and time, right? So if I plot with respect to x, it should give me a curve, right? So just imagine if it is multi-valued and you are solving the Schrodinger equation at a particular point, you will get two different values. So it's very absurd. Imagine a particle being at two points simultaneously. Like that absurdity will come from double slit experiment, but that's different case. Fundamentally, we should not put this double valued solution to Schrodinger equation, right? It should be continuous, it should be differentiable, and this should be single valued. That is the criteria for wave equation, right? From quantum mechanics, you must have studied this. The wave function should be continuous. All of these three curves are continuous, and it should be differentiable. This one is not differentiable because it's suddenly changing from here. So this is not differentiable. This is differentiable. This is differentiable. This is also not differentiable. You see, at this point, it is discontinuous. So discontinuous functions are never differentiable. It will show absurd behavior at this point. So it's discontinuous. Its slope will be in every direction. So basically, it will be undefined at this point. Okay. So what is the problem with this graph? This is discontinuous. All other cases are continuous. So all our other cases are acceptable for this continuity case. The next condition is it should be differentiable. So it's not differentiable, then we can't take it as solution. The next condition is it should be single value. You see, this is single value. For each values of x, there will be a single value of psi, right? If you imagine this y-axis as psi, it will be single value. But if you see this case, for this particular values of x, you will have two values of psi, right? If you solve the Schrodinger equation, you won't know which values of psi you will get. You can get this one or you can get this one, but it's very absurd, right? Sometimes you will get this one, sometimes you will get this one. So it's not acceptable. So it should be single value. So the correct answer will be this one, right? This is continuous, this is differentiable at all the points, and it is single valued at all the points. Understood? Anybody, are you having a hard time understanding this? You just can ask me. Okay, I am assuming all of you understood because it's basic basic knowledge about quantum mechanics, and we are studying spectroscopy now, so you must know this. Okay, then which of the following wave function can be a wave function? Any guess?
Sin x.
Yes. What is the problem with 10x?
Discontinuous.
Right. And cotangent of x?
Same reason, they're all discontinuous.
Yes, right. What about second of x. Same reason. It's also discontinuous, right? So sine of x continuous, all others are discontinuous. And if you can differentiate sine of x, and it is single valued also. You won't have multiple values at same point. So the answer will be sine of x. This is basic. Okay, moving to the next question. Okay, the Schrodinger wave equation is mathematically describing which of this quantity. Can we get energy of electron from Schrodinger equation? If I assume the wave function describing electron, can we get energy of the electron?
Yes, sir.
Okay, and momentum?
Yes, sir. All can be mathematically described.
Yeah, correct. So do you see the Schrodinger equation? All these operators are there. There is Hamiltonian, so you can get energy or the time derivative. It describes energy of that wave function. You have this momentum operator, um, this del over del x. So you can calculate the momentum also, and position just apply x on this wave function. You will get the position of the electron. So all of these answers are correct. Okay, let me ask you, can we measure the position and momentum of electrons simultaneously?
No, because that would go against the uncertainty principle.
Yes, correct. So if we try to measure the position of the electron, then eventually we will, what is the measurement process? We will put some light on it and we will observe it, right? So it's a uncertainty in measurement, but fundamentally uncertainty is there statistically actually. So it's just not in measurement process. If you see particles in nature, they are fundamentally behaving like that. So, mm, so you can't do simultaneously some things. So mathematically, can you say like if two operators are commuting, commuting means their commutation relation will be 0. Okay. So can we measure those two variables simultaneously? Let's say A is the operator and B is the operator. Their commutation relation is 0, giving 0. So can we measure them simultaneously? Answer is yes, we can measure them simultaneously. The operators which are obeying this commutation relation are will have the same wave function actually, the same set of wave function describing their property. So let's say A and B, they are obeying this commutation relation. That means I can apply this A first and B second on this wave function, and I can do the reverse. I will apply B first, then A on that wave function. The answer will be same. So I can measure the operator A and B simultaneously because they will have same set of wave functions. Okay, but if you say see this commutation relation of x and px, that means position and momentum in the x direction. If you try to calculate the commutation relation, you won't get it 0. It will be some non-zero value. It will be IH cross. So it's non-zero. So in that case, their wave function to measure those quantities won't have the same set. So they will require different set of wave function to measure those parameters. So in that case, that wave function psi can't be if I apply x and px on that wave function. Let's say I apply momentum first. I try to measure the momentum first, then the position of the particle. Let's say electron, whose wave function is psi. I am measuring its momentum first, then its position. I'll get some value, right, for momentum and position. Let's imagine the reverse. I'll measure its position first, then its momentum. Will it give the same value both of the time? Any guess? First I'll measure the momentum of the electron, then I'll measure its position. That means I'll operate px first, then x on that wave function, right? Then in other case, I'll operate x first. That means I'll measure its position first. Then I'll operate px. That means I'll measure its momentum in x direction. Will those two scenarios will be equal? Any guess?
No.
What will be the difference?
IH cross.
Yes, correct. They will differ by this quantity IH cross. So this IH and this H cross is which is Planck's constant. This is the fundamental nature of particles showing. So fundamentally it will differ by this H cross. So minimally they will differ by this H cross. So if you measure their difference in those two scenarios, it will always be greater than or equal to this parameter value IH cross. Okay, so position and momentum, they won't have same set of wave functions. So we can't measure them simultaneously. If a commutation relation is non-zero, we can't measure them simultaneously. If the commutation relation is giving zero value, then we can measure those two parameters simultaneously. Okay. Moving on to the next question. The Schrodinger wave function is a linear differential equation. Is it correct or not? Is Schrodinger wave function linear? What is Schrodinger equation? Tell.
Yes, it is a linear differential equation.
Yes, because those operators we can operate on this wave function psi, and it will be linearly distributed. That psi function will be linearly distributed among those operators. Like there are two operators, d over dt and del square over del x square, right? There are two operators. If I operate those two operators on the wave function, what will happen? That wave function will be linearly distributed among those operators. So the Schrodinger equation is linear, and there is derivative in that equation, so it's differentiable equation. So it's linear differentiable. So the first answer is correct. Second one non-linear, so it's not correct. C is second order equation. Is it correct? Is Schrodinger wave equation second order?
No.
Why not? There is a second order derivative, right? Del square over del x square.
But there's both with respect to time. I mean, not time.
Yeah,
Like
correct.
the first.
Yeah. If the time derivative is also in second order, then we can, in principle, combine that time, or we can convert that time into space footing. Like we can multiply c with time, then it will be in space dimension, right? So do you know about four vector notation?
No, sir.
Okay, so if it okay, then just take it as an answer. If that and the equation is second order in time and second order in space, we can put the time in equal footing with space. Then that variable we can write as a single kind of variable, like spatial kind of variable, where this time will be the fourth component of that parameter. That in that case, that differentiation we can write as uh, uh, with a single parameter like x mu, where this mu runs from 0, 1, 2, 3. Okay, so this 0th component will be ct, the speed of light, times t, which will be dimension of space, and that other parameters 1, 2, 3 will represent x, y, z. So in that case, I can put time as equal footing of space. So in that case, I can compactly write the actually not Schrodinger equation, Klein-Gordon equation. There is a equation in second order time and second order space. I can compactly write that with single variable. So in that case, that wave equation will be uh, second order differential equation, because that will depend on a single variable collectively, I am saying. So in this case, there are two kind of variables, time and space. One is in second order, one is in first order. So we can't say it's a second order wave equation. So it's not second order, so it's not first order also. It's just mixed differential equation, which is just linear. Okay, so the answer will be the first one. Right.
So,
Yeah.
you had asked some particular vector notation. Could you tell the name again?
Vector notation, just for this question, you were asking, or previously
Yeah.
I
For this question, you asked if we knew a particular vector notation and you
yeah,
gave a name.
that's a four vector notation. Like you can, in that notation you can put time in space footing. You can just multiply speed of light with time, then it will be in spatial dimension, right? So speed of light is meter per second, and if you multiply time, then it will be second cancelled, it will be meter dimension. So in that case, we can put this time coordinate in equal footing of this space coordinate, right? So in that case, you can just assume this time coordinate as a fourth component of this spatial coordinate. So in that notation, it's just another coordinate, another component of that same space. We call it a space-time coordinate. So it's Minkowski notation, where this time will behave as like we can put time coordinate in space footing, and we can compactly write them as a single parameter x mu. This mu will run from 0 to 3. 0 component is time, and other components are space component. So in that case, we can, some wave equations are there, we can write them compactly. So we can say that those are first order, second order. Like if we are talking about Dirac equation, it's first order. If we are talking about Klein-Gordon equation, it will be second order. But for Schrodinger equation, we can't do the same operation. So it's a mixed equation. We can't say it's second order, first order. It's just linear differential equation. Okay. Okay. Then moving on to the next question. Okay, the square of wave function's magnitude is referred as, and guess, you might be knowing this, don't have to guess. Mod psi square, what is this parameter?
Probability density.
Yes, right. So how can we get probability from probability density? If you do the mod square of wave function, we will get probability density, right? It's just density at every point of space and time. So it's a probability density. How we will get probability from that probability density? It's simple. Just we have to square the probability density. It will give probability. Right? You understood this? You might be doing some quantum mechanics problem solving where you get the probability density, then you square it, then you will get the probability of that particle. Probably you know this, or we can do some numericals in next class to solve this. Okay, so the square of this wave function will represent probability density. Okay. Okay, so it's basically the same question. Okay, what is the physical significance of this psi square? That's probability density, right? I have to put a mode which can be complex. So mod square of psi. It's probability density. If it is 0, what is the meaning of that? If mod of psi square is 0, what is the meaning? What can we understand from that? Remember, we can get probability from probability density. So if probability density is 0, then probability is also 0, right? So let's assume you want to measure the position of particle whose wave function is psi. So if this psi square is 0, that means probability density is 0. That means probability of finding that particle is 0 at that position. This psi depends on position and time, right? So you can say at that position particle can't be found at any time, right? If it is giving some positive value, then so it can't be negative at all. So if it is giving some large value, this mod psi square is very large, then what can be understood from that? If you want to measure the position of that particle, then what can be understood from this? If this mod of psi square is very large, let's say it's 0.8.
The probability of finding the particle at that position is very
More.
high.
Yeah, right. So that means the particle will be staying in that position for a long time, and if we try to measure its position, we can, most of the time we will find that particle at that position most of the time, right? Now say this mod of psi square is 0.2, less than that 0.8, right? Then in that case, what is the intuition we will get from that? If we try to measure that particle, then 20% of the time we will find that particle at that point. 0.8 means the probability is 0.8 means 80% of the time we will find the particle at that position, because it will be staying in that position most of the time. And if this let's say not probability density, probability is 0.2, then that means 20% of the time we will find that particle uh, in that position, right? That's the physical significance of this um, psi square. Psi itself does not have any meaning. We can't comprehend this wave function physically and with anything. We can't associate that wave function with um, any observable psi. Like if you observe anything surrounding you, you can't just associate that wave function. It's not a physical wave. It's mathematical tool we use to do a calculation. So psi itself does not have any meaning. Other hand, this psi square have meaning. It describes the probability density of that particle. So from that psi square, we can get position and moment, all other, or simply just probability of getting that particle, right? Or just like so. As I see, I am out of question now. In this position, we can do some discussion, or you can ask me anything about the class or any question you have in mind. Okay, let me ask you something. Okay, let's assume initially there is a state. You might be knowing about bra state and Kate state, right? So initially there is a state psi of 0. Okay. So after some time you want to measure some observable operating on that state. So what will be the form of that state after some time t? So initially at time equal to 0, that initial state was psi 0. Okay. I can write that. So after some time t, what will happen to that state psi of 0 state? In case it it will evolve with time, obviously. So that means what? That state might change. What will happen to that state? It will go through some time evolution. Let's say t equal to 0, the state was psi of 0. After time t, how you will describe that state? Let's say if I apply this energy operator Hamiltonian on that state psi of 0, I will get energy E1, right? After some time I will operate that same Hamiltonian on that state. What I will get? What will be the eigenvalue I will get? You can guess anything. It's supposed to be a discussion. I just want to know.
You get different eigenvalue.
Sorry?
A different eigenvalue for after it evolves in time.
How it will evolve? That's my question. After some time, what will be the form of this wave function? Let's assume it's an eigenwave function. Okay. So after some time t, what will happen? Do you know about unitary operation? I already gave you one hint. Like if you apply this Hamiltonian operator on this psi of 0, you will get E1 energy with the same state. Okay, so it's a eigenstate. So its eigenvalue, energy eigenvalue is E1. So after some time, what will happen? How it will evolve? Schrodinger wave picture. Do you know this unitary operation e to the power minus I h over h t over h cross? It is being taught in third class of this course, time evolution of wave function. So, initially the time t equal to 0, if the state is at psi of 0, after some time that wave or that state will change to e to the power minus I eigenvalue of that Hamiltonian, that means energy E times t over h cross into that same state psi of 0. Okay, so the psi of t will be you can just write it down, and you can see it will be evolving with time, with this operation, unitary operation e to the power minus I e t over h cross multiplied with that psi of 0. Okay. So it evolves with time. Say so it's evolving. That state is evolving. So in this picture, the state is evolving with time, and in this evolving of state with time is known as Schrodinger picture. Okay. So in another scenario, you can imagine that state is not changing, but the operator which we are applying, that is changing with time. So what we call that kind of picture? Do anyone know? Like previously it was that state was evolving with time. Now the operator itself is evolving with time. It has a name. This picture is has some name. The evolution of state is known as Schrodinger picture. Then the evolution of operator itself is known as Heisenberg picture actually. So in Heisenberg picture, that operator itself evolves with time, and the state it won't evolve with time. In Heisenberg picture, the operator evolves with time. But in Schrodinger picture, the operator itself do not depend on time. Only the state is evolved. It evolves with time. Okay. There is something else in between, like interaction picture, where okay. Okay, in the interaction picture, that operator it will be evolving with this unitary operation, like u some operator u dagger. This u will have the form e to the power minus I some operator time variable divided by h cross, that kind of form. Okay, so that's some different scenarios in quantum mechanics. What else? Like, let me ask you something. There is an operator A. I want to check its evolution after some time. Then if I operate d over dt to this operator A, how will you quantify that? Do you know any formula for that? dA over dt, where A is the operator. What it will be equal to? If it does not depend on time explicitly, let's say this operator A does not depend on time explicitly, that means that partial differentiation of this operator with time will be 0. But this operator will evolve with time, that absolute differentiation dA over dt will have some form. There is a formula for that also. It is being taught in classes in week 1 also. Do anyone remember? Do anyone remember about the commutation of that operator with the Hamiltonian?
Yes.
Yes. So this evolution of that operator dA over dt will be equal to some constant like maybe IH cross and then expectation value of the commutation relation AH. So you see where there will be time differentiation time involvement, there will be coming energy itself, because that operator itself describes the energy of that wave function or particle, whatever you can say. So if you see the time evolution of an operator, then there will always be that Hamiltonian interaction with that operator will be coming. So the time evolution of that operator A is there. That means we will be measuring time. We will be measuring energy and the expectation value of that operator itself simultaneously. So it's like commutation of A with Hamiltonian. So if the commutation relation is 0, then what will happen? That commutation of A with H is 0. Then what can we say about that operator?
Both H and A can be measured simultaneously.
Yeah, that's correct. What other things we can say? That is 0, right? Then commutation is 0. Then left hand side dA over dt is 0. Then what can we say about this operator? So differentiation of some quantity is 0. That means it's a constant in with respect to that variable, right? So let's say differentiation of something with respect to x is 0. That means it's a constant with respect to x. So it's not changing with respect to x. So that means dA over dt is 0. That means that parameter is not evolving with time. Right? Its derivative is 0. That means that parameter itself is not evolving with time. It's constant. As time progresses, that variable, that operator will remain constant. So if you want to measure that variable at time equal to 0, you will get some value, and after some time passes, if you want to measure that same variable, then its value will remain constant. So it does not depend on time, right? So if I give you wave function, or let's say wave state ket vector, and I will say, can you tell the position of that particle associated with that wave? How can you measure the position if I give you a wave function or that ket vector? How to measure the position? What does this expectation value of a parameter mean? Do you all know about expectation value of an operator? what will be the
It is
expectation? Yeah, what will be the expectation value of x? If I give you this ket vector psi, how will you, in formula, how will you write the expectation value of x? What you will do? How do you write expectation value of x? If I give you psi as ket vector, then what you will do? Bra of psi, then x operating on the ket of psi. What is this quantity? This is the expectation value of that operator x, right? So what does this expectation value mean? Does anyone know? When you say measurement of position, how do you do measurement? If I give you a function, how do you measure its position? Absolute position.
average value.
Average value of yeah, expectation value means average value of that parameter. So what does that mean? Most of the time when I try to measure that position, I will get the same answer. Let's say if I want to measure, let's say there is a particle inside a potential wall with length L, and I want to measure its position. Then its expectation value is giving me value like L over 2. Then what does that mean? Then that means that particle will be found at L over 2 distance most of the time, right? Measurement means you will operate that bra vector, you will sandwich that operator between a bra state and a ket state, right? If you want to measure the position, then you will sandwich that operator between a bra state and a ket state. Okay. So if you want to measure momentum, let's say, what you will do? You will apply this bra state on left hand side, then you will operate this momentum operator del over del x with some constant and ket vector, right? The value you will get is the measurement of that parameter, let's say momentum. Okay. Okay, so that's the expectation value. And do you know orthonormality condition? Say that I give you a set of ket states, let's say psi 1, psi 2, or just ket of 1, 2, 3. So if I do the inner product 1 with 1, then it will give 0 or non-zero value.
Zero value is their orthogonal.
Yes, if it is giving 0, then it's orthogonal. I am doing inner product of 1 with 1. Let's say 1 is a state, similarly 1, 2, 3, 4 are states. Okay, so I am doing inner product of one state with itself, then it will give 0 value or non-zero value. Or you say just few continuous generate 1, 2, 3. Psi 1, psi 2, psi 3 states are there. If I do inner product of psi 1 with itself, that means bra of psi 1 with ket of psi 1, so it should give me 0 value or non-zero value. inner product means projection actually. So you might be knowing about dot product of vectors. So what does that mean? If I am doing dot product of a dot b, there are two vectors a and b. If I am doing dot product, then that means I am projecting one vector upon another vector. Okay, so if just imagine there are two vectors with some angle theta. Okay, I am doing dot product of those two vectors, then that means I am projecting that vector upon the other vector, right? If that a and b I am putting parallel to each other, that means I am overlapping a and b, then in that case what will happen? The projection length will be the vector length, right? So it will give me non-zero value. So let's say this is the vector a. I am doing dot product of a with itself. That means I am overlapping a with itself. That means the projection will be the length of that vector, right? So it will be always non-zero. That inner product means in vector sense you can imagine it as dot product of two vectors. Or in that case, inner product of two states means like if you imagine those as vectors, then this inner product can be imagined as dot products. That means projecting one vector upon another. So if it is giving 0, let's say this there is a vector a or psi 1 and there is another vector psi 2. Their inner product is 0. That means what kind of information we are getting from that? If their inner product is 0, you can imagine it as dot product, right? I just said. So if it is 0, then that means what? They are perpendicular.
They're all
Yes, they are orthogonal to each other. So the angle between them is 90 degrees. So if you project one vector to another vector, projection means shadow. Just you can imagine as putting some light on one vector and you are projecting its shadow to another vector. In case of 90 degree, then it won't project any shadow to other vector, right? In that case, that vector is orthogonal to the other vector. So in quantum mechanics, we deal with orthonormal vectors. That means what? The inner product of a state with itself should be 1. That means it is normalized. Why do we need normal vectors? Any guess? What will happen if I do not normalize it? What we calculate from this states? We calculate probability, right? So if it is not normalized, then probability of getting some value will be more. It can be more than 1. That means what? Let's say if I want to measure a position of the particle, then its probability of getting that particle at a point is 1.2. That means what? There is 120% chance of getting that particle at that position. Does that make any sense? How can we imagine 120% chance of getting a particle at a position? We can't imagine that, right? So maximum the probability can take value 1, right? So In that case, we have to normalize the state. Otherwise, it will give absurd results. To conserve the probability, we need to normalize the state, and um, the states, the collection of states, they should be orthogonal to each other. So, like in coordinates, Cartesian coordinates, x and y axis, they are orthogonal, right? So, any vector on that xy plane, I can write as linear combination of this x coordinate and y coordinate, right? If those x and y axes are not orthogonal, let's say there is some arbitrary angle between them, and I want to write vector with respect to these coordinates, there will be some multiple ways I can write it. The coefficient can be how do we write a vector? Some constant a times that x direction or I k plus b times j k or y direction, right? So if those are not orthogonal to each other, let's say they are having some arbitrary angle between them, then in that case I can write a value can be anything and b value can be anything. I have more freedom to I can take any set of values and I can write that vector in terms of this a and b if they are not orthogonal. But if they are orthogonal, there is a unique way I can express that vector in terms of those orthogonal axes, right? So similarly, in quantum mechanics also, the states which we will have should be orthogonal. Otherwise, what will happen? Uh, like when you try to measure something, so what you will do? You operate on uh, that wave function, right? So if they are not orthogonal, then you will get some absurd results, like um, it will be simultaneously in both of the states. Measurement is what operation on state, right? So if I operate on state, then it should give me some results. If those are not orthogonal, I can always write the one axis with another axis. Like if they are not orthogonal, I can write x in terms of y also. They should be orthogonal, so that I can't write x axis in terms of y axis because they are orthogonal, right? I guess you are understanding. Um, okay, so the states, they should be orthogonal. No? That means they should be perpendicular to each other, and they should be normalized. That means their magnitude should be 1. If they are greater than 1, then it will give us absurd results, like probability can be more than 1. So for that case, um, we have to normalize them, and we have to have some finite number of states. Why is that? Can we can have infinite number of states also, but we need a finite number of like complete set of states, so that the probability should be conserved. Like you know about the outer product of the states, the summation of outer product of the states, it should be identity. It's a completeness principle you might know from the quantum mechanics, basic quantum mechanics postulates. Okay, so as I didn't have any questions and I can't write, I talk this one. So do you have any questions? from class or in general from quantum mechanics that you want to ask now. So if not, you can always mail me if you have any question. I'll reply, and I promise I'll do something to write on the screen in next class. That would be better, better interaction class. So sorry for today, and I guess I'll see you in next class if you don't have any questions for today's class. Is that okay?
Yes, sir.
Okay. So feel free to write feel free to write mail to me if you have any question. Okay. So see you in next class. Bye then.
Thank you, sir.